This video is about optimize selection. This operator allows attributes to be added or removed from an example set whilst evaluating the performance of a classifier or some other operator with the objective of finding the optimum number of attributes that maximizes that performance. This can be a useful way simply to improve the performance of a process in general, but also it allows processes to run more quickly by virtue of having potentially fewer attributes. The optimize selection operator has two modes of operation, either forward or backward, and there are various parameters to fine-tune that. The algorithm employs a greedy, or otherwise known as a locally optimal search, so it's not guaranteed to find the best globally optimal solution. Nonetheless, it's pretty good. So we'll look at various topics. We'll look at the selection direction parameter, forward or backward. We'll then do a very detailed step-by-step walkthrough of forward selection. This will involve using the log and logged data operators. We'll quickly illustrate backward selection, and then we'll finish off with some of the other parameters. So we have a process. This process makes some data. Details don't matter, but the data I'm using is called the Sonar dataset, which is available in the repository, and I'm making 2 copies of it. I found a reference in the literature to that data. Here it is. The top flow goes to a cross-validation operator where a model, k nearest neighbours, is used to estimate the performance of that model on the data in general. I'm doing this simply to see what happens if you use all of the attributes. The bottom data flow is the same data, it's just a copy, goes to the optimize selection operator where the process is run, and what we'll do is turn the log entries that are written inside this operator. We'll turn those log entries to an example set using the log to data operator. This generates a new example set here, but the output from the optimized selection will simply flow through the log to data operator here, so we can examine them at the end. But when we walk through the optimized selection operator, we're actually going to go right inside it. But anyway, first thing, let me run the process and look at the output from the estimate on all the attributes. So the performance vector for the top row is here, 80%. So basically this is saying that the k nearest neighbours model should get about 80% when it sees unseen data. Not bad, but can we do better? And this is really what the optimized selection operator will help us look at. So let's go back to the design view. If we look inside the optimized selection, so basically inside that there's a validation, cross-validation operator. This is exactly the same in fact as the one outside. It's a k nearest neighbours, n is 3, k is 3 rather, apply model and performance. And what I'm doing is I'm using the log operator here to record some information about what's happening. This sub-process operator is just in the way, really. It's just a way of me setting a breakpoint on the log operator so I can examine those outputs. You don't need this. You also don't really need the log operator. I'm merely including it so we can see what's going on. So what's going to happen is when the optimized selection operator runs, the inner operators are called. First time through, the optimized selection operator starts with the first attribute, selects that with obviously the label, and passes it to the inner operator. This inner operator, the first one, the cross validation, will build a model and determine a performance for that model and output that. The performance is essentially then passed upwards back to the controller of the optimized selection operator, where it remembers that performance and will start again, but this time with the second attribute. This second attribute will then have a model built on it and a score will be created. This score, this performance, will then be compared with the previous one, and if the performance is better, it will remember that, and it will keep repeating this for all of the attributes. Now the sonar data has 60 attributes, so this will repeat 60 times. After this first pass, then it remembers essentially that the attribute which gave the best performance, and then it will start again, this time with 2 attributes. The first of those attributes will be the one that was best from the first pass through, and the second attribute will be selected sequentially from the remainders. So by this method it will then it'll try 2 attributes, but there will be obviously for the sonar there'll be 59 attempts at that. The best pair, the best performing pair, will then be remembered, and then the process will repeat for 3 attributes, where the first 2 of these 3 will be the best pair, and then the third attribute will be one of the remaining now 58 attributes. This will then keep going until there's no more attributes left. Or obviously there are some parameters that you can change to exert some control over that, but for the sake of argument, let's just run it all the way to the end. So anyway, best thing to do is to actually look at the log operator to see what I'm recording, and then we'll breakpoint through this and see how it works. So what I'm recording in the log operator are various things of interest as we proceed along. So I'm recording the validation apply count. This is the number of times the validation operator has been called. We should see that incrementing, 1, 2, 3, etc. Validation performance, that will be obviously the performance of the validation operator on the training data that it sees. Optimized generation, this is the value of the generation that the optimized selection parameter currently is at. Now generation in this case is the same as the number of attributes, I guess. So in other words, the number of generations you get will equal the number of attributes that there are in the original example set. That essentially represents a maximum. So you'll see that incrementing as more and more combinations of attributes are tried. Optimized feature names, this is the best performing set of attributes that it has encountered in the optimized selection parameter. Optimized selection operator. And then finally optimized performance, this is the best performance it's seen as it goes through. So what I'll do is if I break on the log operator and let's run the process once, and we'll break now the first time inside the optimized selection operator. So what you're seeing here is this is the first time in, attribute 1 has been selected. There were 60 attributes in the sonar data set, and the label's been selected, and there are 208 examples. So far so good. A model has been built, and when it's applied to the training data we get this performance, 53.86, not very good. If we look at the log, table view of the log, you can see that that has been recorded in the log, and you'll ask why are these question marks, and these are simply because the optimized selection operator hasn't had anything returned to it from its inner operators, so it doesn't yet know what the best features are, the best performance. But we do know that the validation operator has been called once. It returned a 53.9% performance, and it was the first time. We're now currently in the 0th run of the optimized selection operator. If I run this again, now what you're seeing is this is the second attribute 2, a model, this time 51.42%. Now the log has 2 entries in it. So it was the first one. Now the second one, which is the one we're on now, has essentially recorded the details of from the log, from the breakpoint we just stopped at, but it's also remembered the 2 current best attributes and performance. I run it again. Now it's attribute 3 that's being considered. Performance vector 49.03. Look at the log. Sure enough, 49. There it is. Attribute 1 is still the best. Keep going. I'm going to go. I happen to know it's at attribute 6, so I'm just going to break 3 times. Now, if I look at the log, attribute 6 is being considered, or has been considered. It performed at 54.31. Now, if you remember, that's actually better than attribute 1. So now, if we look here, we are here. We've just done this measurement. We've seen 54.3. We knew we were on attribute 6. So we know that the next time we run, attribute 6 will become the best. If I run it, look at the log. Sure enough, attribute 6 is now the best that it's seen. And it's just done the attribute 7 measurement, which is worse. So if I go back to the design view, if I take that breakpoint off and just let it continue, as it runs, you can see that the log file is being written to. If we wanted, we could plot this in real time, but I'll wait until the end, and I'm going to convert this to an example set, which makes it a bit easier to manipulate. But you can see, you can sort of get a sense as to what's happening. You can see it found that these attributes were suddenly better. Anyway, so here we are, it's finished. So let's look at the log to data. So this is what we saw in the log. Sure enough, it was attribute 6 getting better. And you can see as we scroll down, after a while, after it had been through all of the permutations, all the possible combinations of attribute, it decided to move on to pairs. You notice here, this is where it started looking at pairs, and it's only when it got to attribute 5 in combination with attribute 12, which was obviously the best one from the first run, the first pass through, did it decide that the performance was better. But we can see this quite neatly. If I do this view here, this is showing the feature names, the best feature so far along the y-axis, and the optimized performance along the x-axis. And you can see as it goes up, the performance is getting better and better and better, and you can see it's selecting more and more attributes. But there comes a point, and I've coloured the point in by the optimized generations, which will go between, as you can see, a 0 and 59, i.e. there are 60 generations. So as it goes up the generations, it gets to the point where it can't do any better, which is this point here, and then what's happening is it's not remembering any better attribute combinations here, and the generations are increasing and going redder, so you can see there's a redness happening here. So it's quite a neat illustration of what's happening. So it starts off and it sort of ascends here, and then at this point here it's at 92.5% roughly. It says the best combinations of attributes it's found is these here. And we can see if we look at the performance vector now that's come out from the optimized selection operator, 92.3%, very good. The example set that's output is actually the example set with the attributes corresponding to that best performance. You can see them there. There's also some weights output. If I do that, those weights are set to 1 if the attribute is to be selected, and then you can use the select by weight operator. This is another video to choose those if you need to. So all in all, it does quite a nice job. And if we just draw this another way, if I change this to be the generation along the bottom and the optimized performance on the x-axis, you can see, so along the y-axis, you can see that it's essentially moving along. Each generation the performance is getting better and better, and then it sort of plateaus and then settles down slowly. Now if you remember, the performance that we did on the very first run through, which is this here, 80.27, I would expect that the performance should be about the same there. It's not quite, there's some subtle difference. Can't quite explain it. It's probably to do with random numbers. You can see that the performance gradually, as you increase the number of attributes, settles down to the performance we observed when we ran it against the whole example set earlier with all the attributes in. So that's forward selection. Now obviously we can do this, backward selection. If I run that again. So this time the log to data in this situation, so I'm now plotting the generation along here, and the optimized performance is sort of the mirror image of the first one, so it's found the same basic point, but it's starting from the back. So it starts off with all of the attributes and it eliminates one by one, and it's essentially found the same maximum, and then eventually it goes all the way down to one attribute. So that's quite neat. Let's look at these parameters now for the optimized selection operator. So let's just deal with these one by one. Limit generations without improvement, I think it should be in English. This basically lets you stop early. If you set that to true, it will, I've picked a number 5 here. If I ran that now on the forward selection, we'll find that the peak will be found, and then 5 generations after that will be attempted. We should get the same answer. So for example, log to data, charts. So sure enough, it's found a peak. I think it was that one, and there's 1, 2, 3, 4, 5 generations after it, and it said, right, that's enough. I think I found a maximum. There shouldn't be any more after this, so I'm going to stop. So that's just a way of making the thing terminate quickly, which is often a good thing. The limit number of generations, this is this parameter here. So if you think you're going to get an answer within 10 generations, you can make it stop. So after 10 in this case, or whatever number you choose. So again, if I run that, it should be a bit quicker. Sure enough, log to data, chart. So there are 10 generations, 0 to 9. So obviously that's useful if the process inside the optimized selection is quite laborious, quite labor intensive, quite time consuming, then sometimes it's worth just limiting the number of generations. Keep best is a way of making the search less greedy. So if I set that to 2 and run it, I'll have to pause the video because it'll take some time. So now what it's done is it's run against all of the attribute combinations it can think of, but instead of just remembering the best each time, it remembers 2 best ones. What it means is that no longer is it a purely greedy search, it'll actually include other attributes in the consideration. It becomes more of a brute force search in that case. But if you look at you can see it's done that by looking at the data here. You can see that after the first individuals are considered, then when there are 2 attributes to think of, you can see there are more runs where the optimized generation is 1. So if I just show this down, considerably more entries in the log file now, because it's considering 2 possible best features so far. You can also see here the number of examples has increased to 3,600. Previously it was less than that. Normalized weights, that's the output. I tend to leave that alone. It doesn't seem to make any difference. Use local random seed lets you set the random seed up specifically if you want to. Show stop dialog, user result individual selection, show population plotter. I tend not to use them. They tend to pop up dialog boxes, which if you forget cause the process to stall, so I leave them well alone. Population criteria data file. This, I think, I've never used it. I think it lets you write the answer, the output, to a file. And finally, maximal fitness. That, I guess you can set that to be a number where if you think you're never going to get a fitness better than 0.9, then set that to 0.9, because I guess you might be overfitting if you're going any higher than that, so that might be a way to avoid that by setting that explicitly. Okay, so I'll run it one more time. With keep best equal to 1. Now, let's just look at the log file one final time. So the chart view here, if I put the feature names in with the optimized performance, so you can see the progression. Just as a final insight, we look at the examples here. So you remember when I set keep best equal to 2, it came to something like 3,600. With 3,600, with keep best equal to 1, it's 1,830, which if you should be able to work out the number that it should do. That number represents the number of permutations of 1, 2, 3 attributes, so it should be 60 times 61 over 2, I reckon, which is 1830. So anyway, I'll just leave with this final picture, which gives you a nice illustration of how the optimized selection builds up to its final answer.